Hi friends, I am going to explain the details on PN junction diode formed by semiconductors. Let us start with semiconductors and how the diode is constructed and how does it work. Now you are seeing the semiconductor devices. This is PN junction diode. From that basic concept, the remaining devices are made: Zener diode, laser diode, PN junction solar cell, light emitting diodes and photodiode. You can see the tabulation here. It explains the types of semiconducting materials. These are available in different types like elemental form, binary compounds, ternary compounds, quaternary compounds and so on. In elemental form, the fourth column, silicon and germanium are most commonly used semiconducting materials. Now, let us see how the solids are classified. Generally, solids are classified based on electrical conductivity. There are three types, namely good conductor. Good conductor means a substance which conducts electricity freely, for example, all kind of metals. The second one is bad conductor, means a substance does not conduct electricity freely, for example, rubber, plastic and wood. The third one is semiconductor. This substance having the property of lie in between good conducting materials and bad conducting materials. With respect to external energy or doping, these semiconducting materials having conducting phenomenon, simply we can say it as at low temperature, that is absolute 0, that is 0 Kelvin, it acts as a bad conductor. At high temperature, say room temperature, it acts as good conductor. Next, let us see the classification of semiconductor. So, based on purity, the semiconductor can be classified into two. The first one is intrinsic semiconductor, the second one is extrinsic semiconductor. Intrinsic semiconductor is nothing but the semiconductor is in the pure form, that is called intrinsic semiconductor. Here number of electrons is equal to number of holes. So, the electrical conductivity is very small. Example of intrinsic semiconductor: germanium and silicon, which are in pure form. Next, extrinsic semiconductor is nothing but just add impurities to the intrinsic semiconductor, then it will become extrinsic semiconductor. So, in order to increase the electrical conductivity phenomenon, we just add impurity to the intrinsic semiconductor, is called as extrinsic semiconductor. Next important process name is called doping. Doping is the process that is addition of impurities to the intrinsic semiconductor to increase the conductivity. So, how do we get extrinsic semiconductor? So, adding impurities to the intrinsic semiconductor, we can get extrinsic semiconductor. That process is called as doping. Doping can be achieved by the impurities. The impurities is nothing but chemical elements. So, based on impurity agents, it is classified into two, namely pentavalent and trivalent. Pentavalent is nothing but which has 5 valence electron. Example of that materials: phosphorus, antimony, arsenic and bismuth. Trivalent is nothing but which has 3 valence electrons. Example: boron, aluminum, gallium and indium. Based on doping impurities, extrinsic semiconductor can be classified into p type and n type. So, look at that equation, the first equation: intrinsic plus something which is equal to p type. So, here we have to fit that trivalent material. So, intrinsic semiconductor plus trivalent material which gives p type extrinsic semiconductor. So, what is the example of trivalent? Yes, one of the example is boron. For intrinsic semiconductor, we use germanium plus trivalent boron which is equal to p type. Like n type extrinsic, intrinsic plus something which you have to place it, which is equal to n type. Can you guess what it is? Yes, pentavalent. Intrinsic plus pentavalent material which gives n type extrinsic. For intrinsic semiconductor, example is germanium. For pentavalent, is phosphorus which have 5 valence electrons. So, germanium plus phosphorus which gives n type extrinsic semiconductor. This is the recap. What have we seen? The types of semiconductor. Initially, we start with solid. Solid can be classified into 3: good conductor, semiconductor and bad conductor. The semiconductor, further it is classified into 2 based on purity, that is intrinsic semiconductor, and other one is extrinsic semiconductor. Further, extrinsic semiconductor can be classified into 2, namely p type extrinsic semiconductor and n type extrinsic semiconductor. Next, we are going to study about the structure of semiconductor. This is the single germanium atom. It is tetrahedral structure. That means it has 4 valence electrons. On the 4 sides, it has each electron present in there. When the atoms are close together, one of electron of germanium atom is associated with neighboring atoms. So, now they are sharing their electrons and they make a bond like that. All the sides the individual electron of these two atoms are making or sharing to each other. So, in this way the covalent bond is formed. Finally, we are getting structure of semiconducting materials. For example, germanium. This is for intrinsic semiconducting materials. Here all the electrons are bonded, so the mobility of electrons are not possible. So, we are going to dope with intrinsic semiconductor. This is structure of p-type extrinsic semiconductor. From the intrinsic structure, we removed one germanium atom. Why? Why do we do that? Yes, we are doping. Doping means addition of impurities to the intrinsic semiconductor. Here addition is the ratio of 1:10⁶ atoms. See, inside the green ring, now boron B is replaced. It has only 3 valence electrons. One of the fourth side is not having a pair, so it cannot make a band. Such a place is called as vacant. That place is called as hole. So, in this p-type extrinsic semiconductor, we are having the active charge carrier is hole. So, majority charge carriers are holes, minority charge carriers are electron in p-type extrinsic semiconductor. See inside the green ring. Now, phosphorus P is replaced. It has 5 valence electrons. All the 4 sides they made covalent bond. One electron of phosphorus is not having a pair, and hence it moves randomly. This electron is called as free electron. Here majority charge carriers are free electron, minority charge carriers are holes. Now, we are going to see how to make p-n junction diode. Just before, we knew how to get an n-type and p-type extrinsic semiconductor. So, here the circle with empty referred as hole, the circle with a shaded portion is called as electron. So, in p region or p-type extrinsic semiconductor, majority charge carriers are holes, minority charge carriers are electron, whereas in n-type majority charge carriers are electron, minority charge carriers are hole. When n-type and p-type are brought to each other, p-n junction is developed. Thus, p-n junction is formed. At this junction, no charge carriers present. The very important notations in p-n junction diodes are potential barrier and depletion region. When p-type and n-type is touched to each other, p-n junction is formed. During the formation of p-n junction, the electrons nearby the junction in the n-type are moving to p-type, where the holes are already presented nearby the junction. Hence, the electrons are occupied the holes and they will become ions. Due to the formation of ions, static electric field is developed. In p-type, negative electric field is developed, and n-type, positive electric field is developed. Thus, static electric field is developed, which is called as barrier potential. Here, barrier means the junction, potential means voltage. So, potential barrier is nothing but voltage is developed across the junction. So, there is a inbuilt voltage is called as potential barrier. Now, the depletion region is formed, which is nothing but the region around the electrostatic field. The depletion region presents, the current cannot go through it, because the depletion region is directly proportional to the resistance of that materials. The potential barrier is varied with respect to that semiconducting materials. For example, silicon, the barrier potential is 0.7 volt. For germanium, 0.3 volt. Due to potential barrier, charge carriers cannot diffuse further. In order to mobilize the charge carriers, we need external DC voltage. This applied voltage should be greater than the barrier potential. According to this figure, potential barrier 0.3 voltage is developed internally for this germanium p-n junction diode. So, we require more than 0.3 voltage for applied voltage. Here DC 1 volt is given to that p-n junction diode, so that the charge carriers can easily break the depletion region. So, external DC voltage is applied, which should be greater than that 0.3 voltage. So, 1 voltage is given to that p-n junction diode as applied DC voltage. So, the 1 voltage is greater than 0.3 volt. So, using this condition, we can move the charge carriers from either sides. Next, we are going to see about the types of biasing. So, we know about that biasing is required in order to move the charge carriers. So, there are two types of biasing. One is forward bias, is nothing but the P region is connected to positive terminal of the battery and N region is connected to negative region of the battery. Whereas the reverse bias, P region is connected to negative terminal of the battery and N region is connected to positive terminal of the battery. Here we see how diode is working in forward bias. The diode needs anode and cathode electroplates to pass the current. So, it is mentioned in that diagram. For forward bias, P region is connected to positive terminal of the battery and N region is connected to negative terminal of the battery. Now, the circuit is switched on. The electrons from negative terminal of the battery is reached cathode. At the same time, the holes from positive terminal of the battery is reached anode. In N type, majority charge carriers are electrons. Nearby the cathode, electrons are also there. Both are similar charges, so repulsion should take place. So, the electrons in the cathode just push the electrons in the N type. So, there is a chance to diffuse the depletion region. During the diffusion process, the ions have become neutralized and hence depletion region is disappeared. So, the charge carriers can easily move. At the same time, the holes in the anode just attracted electrons in P type. So, the N type electrons again diffuse to P type by the electrons in the cathode. So, this process is continuously occurred. So, in this way the charge carriers are moving from either sides in forward bias. So, let us conclude that diode conducts the current in forward bias. Next, we come to see about how p-n junction diode works in reverse bias. Here, reverse bias means the P type is connected to negative terminal of the battery and N type is connected to positive terminal of the battery. So, as usual, we are having two electroplates, namely anode and cathode. So, when the circuit is switched on, the holes are moving from the positive terminal and reach cathode. At the same time, the electrons are moving from the negative terminal of the battery and reach the anode. In N type, majority charge carriers are electrons which are attracted by the cathode holes. Like that, the electrons in the anode just attract that holes in the P type. So, nearby the depletion region, so many ions are developed and hence the depletion region is increased. The depletion region is nothing but it's a kind of resistance. So, if depletion region is increased, resistance also increased and hence the current cannot move at all. So, the charge carriers cannot move. So, from this we come to conclude depletion region proportional to resistance, and diode does not conduct the current in reverse bias. Next application of PN junction diode is rectifier. Diode acts as rectifier because it converts alternating current into direct current, because it allows only one cycle of alternating current. Why? Because it conducts the current only in forward bias. This is AC waveform is given into diode as an input. We can have the output as direct current. That means we have only the positive half cycles of the AC signal. In this way, the diode can convert AC into DC. This process is called the rectification. It can be done by diode, so that diode can be acted as rectifier. Next, types of rectifier. There are three types of rectifier, namely half wave rectifier, full wave rectifier, and last one is bridge rectifier. In half wave rectifier, only one diode is used. So, refer the diagram, you know about the symbol. It has only one diode is used. Next, full wave rectifier, there are two diodes used. Refer the diagram. Here we can have a full waveform. Third one is bridge rectifier. Here there are four diodes used. Mostly all the electronic devices are using this type of bridge rectifier. Thank you.